It is easy to picture black holes as giant cosmic vacuum cleaners, mindless gravitational whirlpools roaming the universe and aggressively sucking up any star or planet unlucky enough to get close. But the reality is far more structured. Take Sagittarius A star, the supermassive black hole at the center of our Milky Way galaxy. It packs the equivalent mass of 4 million suns into an incredibly dense space. Stars safely maintain stable orbits around it, undisturbed unless something else knocks them off course. These invisible giants act as massive gravitational hubs, influencing how galaxies assemble and hold their shape over billions of years. Studying them presents a physical paradox. They pack so much mass into such a tiny volume that their gravity overwhelms all other forces. The pull is so intense that passing rays of light get permanently trapped, rendering the object completely invisible to our telescopes. These invisible heavyweights are the central anchors holding our entire galactic neighborhood together. To understand the origin of standard black holes, we look to the life cycle of massive stars. When a giant star burns through its nuclear fuel, it loses the outward pressure that keeps it stable, causing the remaining mass to collapse inward on itself. That specific sequence of events was first calculated in 1930. Subramanian Chandrasekhar, a 19-year-old astrophysics student, realized that any star large enough was doomed to this endless inward collapse. The scientific community firmly rejected the idea. Prominent figures, including the astronomer Arthur Eddington, publicly ridiculed the calculation, insisting that there had to be a law of nature preventing a star from behaving in such an absurd way. The math was sound, but the implications were so extreme that even the world's top scientists initially refused to believe the numbers represented physical reality. If a collapsed star emits virtually no light and traps any light that gets too close, how do we prove it is actually there? We look for the gravity it exerts on its neighbors. Throughout the 1990s, scientists like Andrea Ghez precisely tracked the movements of stars near the center of our galaxy, proving they were whipping around a patch of empty space that was invisibly, impossibly heavy. We can also detect their collisions. The LIGO facility uses these long concrete tunnels to catch physical ripples in spacetime, generated when two ancient black holes crash into each other. Measuring the speed and distance of these ripples allows researchers to calculate the Hubble constant. This number reveals the rate at which the entire universe is expanding. Humanity learned to map the invisible, not by looking at the object itself, but by measuring the physical toll it takes on the surrounding universe. In 2019, the Event Horizon Telescope captured this direct image of a black hole. This asymmetrical orange ring is an accretion disk of superheated gas fighting the inward pull. The dark void is the event horizon, the point of no return where gravity outpaces light. The event horizon is the absolute threshold of observation. Anything that crosses this line is permanently cut off from the rest of the universe. Past that threshold, everything descends toward the absolute center, the singularity. This is a point of infinite density and infinitely small volume. General relativity describes how mass warps the universe perfectly up to the edge. But at this dense core, equations fail. The infinitely small singularity should follow quantum mechanics. However, these two theories cannot mathematically coexist at this scale. The singularity represents a brick wall for our understanding, where the fundamental laws of reality cease to function. This conflict between our major theories led to a disruptive discovery. Stephen Hawking theorized that black holes have a tiny temperature and slowly leak radiation, meaning they will eventually evaporate away over trillions of years. This leads to the information paradox. If a black hole evaporates into nothing, the physical information of every star or planet it ever consumed would effectively vanish. A sacred law of physics states that information in the universe must be preserved. If that data cannot be recovered from the leaked radiation, it means information is being erased from reality. Black holes are the ultimate extreme laboratories. They are the locations where the universe's source code breaks down, forcing us to rethink the nature of reality.